We'll now discuss a particular example of first-order equations that are especially amenable to analysis, to the graphical analysis. So the equations are going to be called autonomous equations. So the definition is going to be as follows. First order ODE is autonomous if it has the following form. If y prime is equal to f of y. So that is, f is independent of x. So any equation like that is autonomous. So for example, examples of autonomous equations are going to be things like this. Y is equal to, y prime is equal to y is an autonomous equation. Y prime is equal to y times 1 minus y, maybe y prime is equal to sine y. Those are all autonomous. And on the other hand, if I have y prime equal to x plus y, the right-hand side explicitly depends on x, this guy is not autonomous. Okay, so let's try to analyze an autonomous equation. So let's suppose y prime is equal to f of y, and let's also assume f and, okay, let's rewrite this. Y prime is equal to f of y, while f and f prime of y are continuous functions of y. So one thing that we can recall from this, so then recall from a couple of lectures ago, we determined that if I want to solve the initial value problem, y prime equal to f of y, y of x0 equal to y0, remember that we saw this, we said that as long as the function f is such that near point x0, it is near the point x0, y0, f is continuous, and its derivative with respect to y is continuous. So if those functions are continuous everywhere, like I'm assuming here, then in particular they both must be continuous near x0, y0, Notice that there is no dependence on x in f, but then I can treat f as a function of two variables which depends on x in a trivial way, right? It's, because it does not depend on x, you can just simply assume that it's a constant function of x. So what we get then is that f satisfies the condition of continuity, which means that any initial value problem is going to have a unique solution, right? So that is our previous result. So that this guy has a unique solution and this would be true for any point x0, y0. And the consequence from that, which we also discussed before, so if any initial value problem has a unique solution, then we said that any two solution curves of my ODE y prime equal to fy, f of y, any two solutions curves cannot intersect. Because if they did intersect, and I use an initial value problem where I start from the point of the intersection, there are two ways to leave that point. So then the corresponding initial value problem will not have a unique solution. And you'll see that this has some important consequences of what we're going to do next. All right, so I'm going to try to attempt to solve this equation graphically, or the corresponding initial value problem graphically. So let's see what can we do. So if I examine this equation here, I can immediately notice that because f depends on y only, I can make this conclusion. So let's note that if f of y is a positive number, then y prime is greater than 0. And so if f of y is greater than 0, then a solution curve passing through the point xy is increasing, right? Likewise, if f of y is less than 0, then any solution curve is decreasing. Any solution curve which passes through point xy. So remember that x really doesn't matter. So as long as y is less than 0, then if my curve passes through an altitude y, then the solution curve must be decreasing. So let me rephrase this again. Now also, let's suppose that f of some value, let's say ys, is equal to 0. Okay, so let's make this number free. If f of ys is equal to 0, then I'm going to set y equal to ys. Y equal to ys is a constant function. Well, okay, if it is a constant function, then if I take its derivative, y prime is identically 0. But then what I got is that for this particular function, y equal to ys, if I take y prime, we just figured out that this is 0, but 0 is, okay, let me change the direction of this. Y prime is equal to 0, but 0 is f of ys, right? So f of ys, I assumed is 0. But ys and y in this case are the same because I assumed that y is equal to ys. So then y prime is equal to f of y for this particular function, which means that that function satisfies my original equation. So therefore, y equal to ys is a constant solution of y prime equal to y prime equal to f of y. And we're going to call such solutions equilibrium solutions. Of my equation y prime equal to f of y. Okay, so then we see that these free facts actually tell us the following. If I'm on xy plane and y is equal to one of these ys's, where f of y is equal to 0, then those are going to be solutions of the ODE. If y is such that f of y is bigger than 0, then solutions should be increasing. If y is less than 0, f of y is less than 0, then solutions should be decreasing. And actually going back to the third case, if f of y is equal to 0, then the function is just going to stay at the same level. So therefore, everything here is determined by the sign of f of y. So where it is positive, negative, or 0. So we can then sketch the following diagram. I'm going to draw a vertical line. And on that vertical line, this would be my y-axis. On that vertical line, I'm going to plot all points at which f of y is equal to 0. In fact, let's maybe do a particular, well, let's see. We'll do a particular example in a moment. So let's suppose that f of y is equal to 0 at a couple of points. Maybe y1, y2. So I'm going to suppose f of y1 is the same as f of y2, both are equal to 0. And maybe I know that f of y is greater than 0 if y is between y1 and y2, and f is less than 0 otherwise. Right, so let's suppose that we have f like that. So then what are we going to get? So at y1 and y2, f is 0. If y is between y1 and y2, then f of y is positive. If y is greater than y2, then f of y is negative. And if y is less than y1, f of y is once again negative. Okay, so but then y prime is the same thing as f of y. So y prime is less than 0. Y prime is greater than 0. Y prime is less than 0. And so therefore that means that any y here must be an increasing function, y here must be a decreasing function, y there must be an increasing function again. So an object like that is going to be called a phase diagram. Okay, now I'm going to try to use this phase diagram to determine how possible solutions of my autonomous ODE are going to look like. So for that we need to sketch again a choice of xy plane. So, and with that, let's see what sort of information we have about ROD. What do we know? We know that f of y1 and f of y2 is equal to 0. So that means that both y1 and y2 are equilibrium solutions, right? So let's note that fact here. y1, y2 are constant equilibrium solutions. And then it is easy to sketch what these solutions are because they're constant. I did not specify whether y1 and y2 are positive or negative. It doesn't really matter. So let's suppose that one is positive and one is negative. So maybe this would be a graph of y1, of y2, and that will be a graph of y1. Okay, so what does this give us? So y1, y2. What does it give us is the following. So let's look now at what happens when y is bigger than y2. If y is bigger than y2, we assume that y prime, our phase diagram tells us that y prime must be negative. If y prime is negative, that means that the slope, actually, I'm not sure why I place the arrows like this, they're exactly the opposite. The function is decreasing here, increasing here, and decreasing there. So the phase diagram tells us precisely what I just said. Functions must be decreasing if y is bigger than y2. So if I choose any point as a starting point of my graph when y is bigger than y2 as a starting point of my solution curve, then the solution curve has to be decreasing because everywhere where y is bigger than y2, y prime is negative. So that means that the solution curve will have to go down. And so what can happen with it as it is decreasing? In principle, two things can happen. Either it is continue going down and it will push through y2 and keep going down. But then if that happens, then what we got is that two solution curves, the solution curve that I'm trying to construct and my constant solution curves are intersecting. And we said that from existence and uniqueness result, any two solution curves cannot intersect in this problem. So that means that this thing that I have drawn here on the screen is impossible. So then the only choice really for the solution curve to proceed is going to go down and then level off, because it cannot pass through, it cannot change the direction, and it cannot pass through y2, so it will have to level off and look like this. So what it must have is a horizontal asymptote y equal to y2 as x goes to 0, as x goes to infinity. And if you continue it in the opposite direction, then the function must be increasing, right? Because increasing to while going to the left is the same thing as decreasing when you go to the right. I'm skipping the details here. In fact, you can have a horizontal asymptote. It seems that you can have a horizontal asymptote at a level higher than y2, but you can actually show that no, that's not possible. But we're not going to consider that here. All right, so if I now choose to start at some point between, let's say, y1 and y2, in this middle strip, what should happen there? There, y prime is greater than 0. So if y prime is greater than 0, that means that your function is actually supposed to be increasing. It's increasing everywhere for any y between y1 and y2. And not only that, but again, these graphs cannot intersect the lines y1 and y2 because no two solution curves can intersect. So then really, the only possible behavior that you will see here is that you are increasing, but then you have to level off and have a horizontal asymptote at y2. And you have to continue increasing if you're less. If you go in a direction which is prior to your initial point, you still have to stay increasing there. So then you'll have another horizontal asymptote at y1 as x goes to minus infinity. Okay, and finally, when y is less than y1, what will happen here? You will have to be decreasing, and again, you're not allowed to penetrate through the line y equal to y1. So then the only choice really is to have a horizontal asymptote y equal to y1 as x goes to minus infinity, and then continue increasing. And so what you see is that we can fully characterize what kind of solutions of our autonomous ODE can have. And that is all based on the phase diagram for the function f. It fully specifies what kind of solutions you should be able to get, so that you can see on this picture. One more thing here. So if I look at the point y2 at y value y2, if we, so let me write this in words. If we start solving our initial value problem at y, which is slightly greater than y2, then as x goes to infinity, y will go to y2, right? So if we start anywhere above y equal to y2, eventually y will converge to y2. In a similar way, if we start solving our ODE when y is slightly less than y2, then what will happen? In fact, exactly the same thing will happen, right? So in the previous case, y would go down to y2. In this case, y will go up to y2. For the point y1, the situation is the opposite. So let me copy this stuff. If we start solving at y slightly greater than y1, then what will happen? Slightly greater than y1 is somewhere here. What will happen is that the solution will push away from y1. And if we start slightly less than y1, then again the solution will be pushed down away from y1. So then in both cases, y goes away from y1. So then we can characterize our equilibrium solution according to these properties. So in the first case, y2 is kind of attractive, right? Because all y's will want to converge to y2 eventually as x gets bigger. And for y1, if we start close to y1, you always would be repelled from y1. So these type of solutions we then characterize in the following way. So we'll call y2 an attractor and y1 a repeller. So any equilibrium point which looks like y2 here is an attractor, and any equilibrium point which looks like y1 here is going to be a repeller. Okay, so let's do an example of this. So let's suppose that I want to construct this picture for an equation y prime is equal to, let's say, y times y minus 1 times y minus 2. So what we need to do per our discussion, first of all, we need to classify it. Is this an autonomous equation? The answer is yes, because the right-hand side does not depend on x, right? So right-hand side is independent of x. Fine. So then I can see immediately where this function is equal to 0, right? So f of y equal to 0 means that I'm solving y times y minus 1 times y minus 2 equal to 0. This has three solutions: y equal to 0, y equal to 1, y equal to 2. So all of those then are equilibrium solutions. Of my ODE. Okay, fine. So then to construct a picture, the entire picture of how possible solutions of this equation will look like, I would need to draw a phase diagram. So phase diagram in this case will look as follows. So this is my y-axis. I need to sketch 3 points on it. 0, 1, 1, and 2. At those points, f of y is equal to 0, like we said. Those will correspond to equilibrium solutions. So now we look at f of y. So in this case, this is y times y minus 1 times y minus 2. So 0, 1, 2. And we have to do a simple algebra here. So if y is greater than 2, then I have three factors here: y, y minus 1, y minus 2. If y is greater than 2, all of them are positive. So that means that f of y is positive here. When I push this between 1 and 2, if y is between 1 and 2, first two factors are positive, second is negative, third is negative. So the product of 2 positive and 1 negative, f of y is negative. If y goes below 1, then I have two negative factors and 1 positive, so the product is still positive, is now positive. And if we're going to go below 0, then all three factors are negative, so f of y is negative. Okay, so then if this is a case, then y prime, which is equal to f of y, right, which is equal to y times y minus 1 times y minus 2, then y prime will have exactly the same signs, right? Positive, negative, positive, and again, negative. And so then y itself must be increasing here, decreasing here, increasing, and then decreasing. So now we can sketch the diagram which will give us possible solutions. And let me actually use a different color here. So let's say equilibrium solutions are going to be in red. Three equilibrium solutions: y equal to 0, y is equal to 1, and y is equal to 2. So let's label those 0, 1, and 2. All right, and then what do we know? We know that when y is bigger than 2, all solutions must be increasing. So therefore, a typical solution should look like this. It's increasing. If I start with another point between 1 and 2, so let's say somewhere here, and then what do I know? I know that the solution must be, actually, let me modify this. If I start somewhere around here, then what would happen? Then the solution must be always decreasing, and it cannot penetrate through the levels 1 and 2, so it must look like this. If I start somewhere between 0 and 1, then the solution must be increasing, right, between 0 and 1, and so therefore the graph will have to look like that, again, because it has to be increasing and it cannot cross 0 or 1. And then finally, the last case, when y is less than 0, if you start somewhere or y is less than 0, then your graph will behave like this. So we're able to reconstruct completely the possible solutions of our ODE. And you see we ended up with 3 points. The point y equal to 2, the equilibrium solution, it repels all the other possible solutions. So this guy is a repeller. Y equal to 1 attracts all solutions, so it is an attractor. And finally, y equal to 0 repels all solutions, so it is a repeller. Let's do one more example of this. Let's try y prime equal to, let's say, sine x. So if y prime is equal to sine x, then in order to find the equilibrium solutions, so number 1, I want to find equilibrium solutions. Those are solutions which make, actually not sine x, sorry, sine of y. So that this is an autonomous ODE. So autonomous solutions I'm going to get if I solve the equation right-hand side is equal to 0. Now, where is sine of y equal to 0? Sine of y is equal to 0 at all multiples of pi, so y must be equal to pi n, where n is an integer. And so the conclusion from this is that we have infinitely many equilibrium solutions. All right. So we have equilibrium solutions. And now we produce a phase diagram. In principle, we'll have to plot infinitely many points on the diagram, but we can just see patterns. So we have y equal to 0 when n is equal to 0, and then multiples of pi. So pi, 2 pi, etc. Minus pi, minus 2 pi, etc. So 0, pi, 2 pi, minus pi minus 2 pi, and then it just continues. And so we're looking at the sine of f of y, which is sine y. All right, so between 0 and pi, what can we say about sine y? It's a positive number. Between pi and 2 pi, sine y is a negative number. Between 2 pi and 3 pi is going to be positive again. Between minus pi and 0, it's going to be negative. Between minus 2 pi and pi, it's going to be positive. And then I can continue like that. Okay, so then what can I say about y prime? Y prime exactly is going to have exactly the same signs, minus, plus, minus, plus. And so then y will be decreasing, increasing, decreasing, increasing again. And so now I can use this to reproduce possible solutions to my ODE. Notice again that we're working with f of y, with functions f, that are always continuous along with their derivative. So I know for sure that no two solution curves can intersect. So let's sketch possible solutions. So we have what? Infinitely many equilibrium solutions, but we're only going to sketch 5. So we have pi, 2 pi, we have 0, let's try it again. We have minus pi, we have minus 2 pi, and so on. So let me fix. Okay. So 0, 0, pi, 2 pi, minus pi, minus 2 pi, etc. And so now we can use the diagram, phase diagram, to determine what the solutions are doing. Between minus pi, between pi and 2 pi, solutions are decreasing. So decreasing and cannot intersect equilibrium solutions. So decreasing, decreasing here, increasing here, decreasing increasing, and then continuing in the same vein as you keep going up and down. And then if we want to classify the equilibrium points, this one is an attractor. This one is 0 is a repeller. Minus pi is an attractor. And clearly minus 2 pi is repeller. And plus 2 pi is a repeller. We did not look at above 2 pi and below minus 2 pi, but clearly the same pattern will continue. And so we can make those conclusions. And so in this case, you will see infinitely many attractors, infinitely many repellers, and they're just going to alternate. All right, so this concludes a section on graphical solving of ODEs, and in the next section, we're actually going to start solving ODEs analytically. As you will see in the subsequent sections, it will be important to remember how to do integration. Remember, as we said in the beginning, that solving ODEs actually involves integrating. And so you absolutely should go ahead and choose your favorite Calc 1 and Calc 2 books and review all the integration techniques, because they will be needed in subsequent lectures and when you will be doing homework. All right, until next time.